Oh. Where am I?
You're in my lair. I've been watching you for some time now, Ryan.
Well, that's not creepy at all.
If you answer these questions,
I'm scared.
you should be. What are the 4 ways to prove 2 triangles congruent to each other? This is the most important because we can use these postulates for 2-column proofs.
Another way to prove these 2 triangles congruent is through the SAS congruence. If side AB is congruent to side FE, and side AC is congruent to side FD, and the included angle is congruent as well, then the 2 triangles are congruent to each other. The third way of proving 2 triangles congruent is through the ASA congruence. If angle A is congruent to angle F, and angle C is congruent to angle G, and side AC is congruent to FD, then the 2 angles are congruent. The final way to prove 2 triangles congruent is through the AS congruence. If angle A is congruent to angle F, and angle C is congruent to angle G, and side AB is congruent to side FE, then the 2 triangles are congruent.
Find the value of z. This is my personal favorite because isosceles triangles are cool and important to know about.
So the converse of isosceles triangle theorem states if 2 angles of a triangle are congruent, then the sides opposite of those angles are congruent. So since we know angle C and angle A are congruent, the sides opposite are congruent. 2z minus 15 equals 9. Since we know AB is congruent to BC, 2z minus 15 equals 9. So 2z minus 15 equals 9. Add 15 on each side, and it equals 24. So 2z equals 24, so z equals 12. To show your work, you have to plug z back into the equation. So 12 times 2 equals 24, minus 15, which equals 9. So you know that AB and BC are congruent. Therefore, side BC is congruent to side AB, and triangle ABC is an isosceles triangle.
Write a coordinate proof for this statement. The segments joining the base vertices to the midpoints of the legs of an isosceles triangle are congruent. This is the most difficult because it's a proof.
Okay, so the given is right triangle ABC with right angle BAC, and P is the midpoint of BC. And we are trying to prove that AP equals half of BC. This is because of the midpoint formula, which is x1 plus x2 over 2 and y1 plus y2 over 2. So we plug in numbers. Now we could draw the triangle. We know that the origin is 0, 0, which is A. And to find C, we want to make it 2C, 0, so that there is no fractions. B would be 0, 2B. The midpoint of BC is P. Now we have to find the location of point P by plugging in point B and C into the midpoint formula. So 0 plus 2C over 2 and 2B plus 0 over 2. This should equal 2C over 2 and 2B over 2. Therefore, C over B. The next step involves the distance formula. The distance formula is radical x1 minus x2 squared plus y1 minus y2 squared. To find the distance of AP, we can plug in the numbers. So radical C minus 0 squared plus B minus 0 squared. And simplifying this would equal C squared plus B squared. So now, since we found the distance of AP, we have to find the distance of BC, which is supposed to be twice as long as AP. So we know that the distance formula is x1 minus x2 squared plus y1 minus y2 squared. So we could say that BC equals 2C minus 0 squared plus 0 minus 2B squared. Simplifying it would be 4C squared plus 4B squared. And this would equal 2 radical C squared plus B squared. So now, since we found the distance of AP, we have to find the distance of BC, which is supposed to be twice as long as AP. So we know that the distance formula is x1 minus x2 squared plus y1 minus y2 squared. So we could say that BC equals 2C minus 0 squared plus 0 minus 2B squared. Simplifying it would be 4C squared plus 4B squared. And this would equal 2 radical C squared plus B squared. So now that we found both the distances, we can compare them, and we can see that the distance of BC is 2 times as long as the distance for AP. So therefore, AP is equal to half of BC.